All right, well, hi everyone. So I'm Jack and I am the new kid here. So I'm very happy to be here in Swansea, starting my PhD on the functional diversity of sharks through time, working with Catalina Pimiento. So before I sort of get into the nitty gritty of what we're going to be doing, I want to talk a wee bit about me, my background and some of the work I've done. I was born and raised in Scotland, and I was brought up in a wee West Coast town called West Kilbride, where I lived with my parents, my twin brother, identical twin brother, and also my cat, Cody, who you can see there on the left. And as you can see from his wee nose and his grey fur, he's still very fluffy and very adorable at the tender age of 12. It was during my childhood in West Kilbride that I first got into sharks, and specifically from watching the BBC Sea Monsters, in which the presenter Nigel Marven would quote unquote go back in time to various prehistoric seas, and he would visit various ancient marine animals. And one of the animals he met was Megalodon, the biggest shark in the fossil record. And to a small child, I was 6, going on 7 at the time. It was immediately captivating to know that such a giant shark had actually existed. And so from there on, I was hooked and pursued a degree in evolutionary biology at the University of St Andrews. And it was during my time there that I actually got to work with sharks directly for the first time, specifically in the form of 2 internships in South Africa, where I was part of the ecotourism industry, and I got to cage dive with and observe great white sharks up close. And I'm gonna actually play a quick 20-second wee video to sort of give you a very brief insight into what life on the boat was like there. So that there was a 3.5-meter female great white shark that we called Flicky. If any of you noticed, she flicked her tail a lot as she turned, which is where the name comes from. But getting to see sights like that shark and these iconic animals up close only cemented my wish to continue studying sharks. But I was more interested in studying ancient extinct sharks, where we mostly have only their teeth to go off of. So I took on a master's degree in paleobiology at the University of Bristol. And it was actually there that my interest in Megalodon came full circle. As for my master's project, I got to work on that very animal under the supervision of Bristol's Mike Benton and Swansea's Catalina Pimiento. Essentially, the aim of this project was to take measurements of specific body dimensions like the head or the fins or the tail of various living sharks and apply them to mathematical modeling so that we could calculate those sizes in Megalodon, which until recently had only ever had its total length calculated. And amongst our many results, we found that the dorsal fin of a 16-meter adult Megalodon would have been about 1.62 meters tall. So I don't know how tall most of you are, having never met any of you beyond a computer screen, but if you're about 5'5", then that dorsal fin is the same height as you are. So this project was completed in 2019 and just recently was published in Scientific Reports, where we got to include all of our various body dimension results, but also a full 2D reconstruction of Megalodon itself, which was beautifully done by one of my classmates. And the incredibly rewarding experience of getting to work on the very animal that got me into sharks, paleontology, and science simultaneously only further motivated me. I wanted to continue studying not just this animal, but also expand my horizons a bit and study more fossil sharks and also what roles they might have in their environment, which brings us to the PhD in the functional diversity of sharks. For those of you who don't know, functional diversity is essentially the elements of biodiversity that link to ecosystem structure and functioning. What this means is that you're not only looking at the species in a certain ecosystem, but you're also looking at various species traits and how they link to certain ecological roles. which means if you were to study an extinction event from a functional diversity approach, you're looking into not just taxonomic loss, but also the loss of certain traits. And therefore that reveals the loss of ecological roles and the relative impact of those losses. Now, sharks are an ideal model to study functional diversity because they have an exceptionally long evolutionary history of over 400 million years. And across that fossil record, you find their teeth everywhere. They are literally the most common fossils you can find in the fossil record. But of more relevance to us is that various traits within those teeth can actually link to ecological functions. For example, the height of the tooth can often reflect the size of the shark, whereas the type or shape of the tooth can reveal what prey it was eating and also how it was eating that prey. But in relation to today's sharks, there are over 500 species worldwide, and that brings enormous diversity, not just in the size of the shark or the prey they eat, but also in reproductive strategy and the habitats they occupy. What this essentially means is that sharks occupy a huge number of ecological roles. They can be apex predators that control the trophic level, the populations of lower trophic levels. They can be part of nutrient cycling, or they can simply remove diseased individuals and help balance the ecosystem. And this is relevant to note because today, sharks are actually among the most threatened marine vertebrates on the planet. They face a wide number of human-related risks, including trophy hunting, shark finning, or even just deliberate overfishing of endangered species. This, combined with climate change-related risks and habitat degradation-related risks, means that between a quarter and a third of today's sharks are in danger of extinction. And to give you a specific example, just last year, the great hammerhead shark and the oceanic white-tip shark both became critically endangered. Because sharks occupy such a wide range of ecological roles, their decline is going to have an enormous impact on their environment. So what we're proposing to do for the next 4 years is we're going to assess shark functional diversity through time by essentially taking their teeth, measuring how traits of those teeth link to ecological function, and then put those into a functional space through time to observe how functional ecological functions have changed or been more favored or disfavored across that time from about 66 million years ago to the present. But we can also apply that to modern sharks and combine that with IUCN status to observe how functional diversity might change in the next 100 years. What we expect to find is that the functional diversity reduction in the next 100 years, which is actually a very short period of time, is going to be much more dramatic compared to the last 66 million years. So because we've only just started this, I'm going to wrap up just by listing our objectives. The first thing we're going to do during lockdown is synthesize existing knowledge of shark dental traits and their ecological association. Hopefully by the time we get to objective 2, the pandemic will have calmed down a bit and we'll get to travel to museums worldwide to measure the traits of extinct and extant shark teeth so that we can determine a range of dental morphotypes, which we can then apply to a functional space through time to assess how shark functional diversity has changed from the past to the present, and finally apply those same morphotypes to today's sharks and IUCN status to forecast how future shark functional diversity may be affected by the threats sharks face today. Thank you all very much for listening. I'd like to thank this large cast of people for their roles in my career so far.